Okay, a very brief epilogue to contingency tables, crosstabs, and chi-square. This is the original problem, the one where we've got Romney, Obama, male and female. I could have mismatched the labels, it doesn't matter. It's 30, 20, 20, 30. You know, the end result, the calculation for the interior of the cells for every one of these turns out to be 1. And the sum of them, the chi-square for the table, the Pearson's chi-square turns out to be 4, with a p-value of 0.045, I believe. It's underneath, just barely underneath 0.05. It's actually going to put, in case we're saying goodbye to the Reverend Bays, I'm going to put his picture up in celebration. Not sure we'll have any more on Bayesian inference, just for relative to time constraints, on video. We'll do more in the classroom together. But I'm talking about this problem as an inference problem outside the context of the frequentist tradition, which is what we did really when we use chi-square and refer to its p-value, 0.045, and suggest then that about 95% of the time that we drew a sample of size 100, we would see an indication that these two variables were not independent. That's the sort of tortured way to make an inference. There's another way. In the Bayesian tradition, this problem would be treated as a model comparison problem, where in one case, in one model, they're independent, the two variables, and in the other, they show a dependency of some sort. There's a deeply related sort of strategy for going about making the inference, but a sort of kind of strangely different process. I want to say something about the process and give you a little bit of code to take a look at it, and maybe something to Google. So once you Google Bayes factor and hit the Wikipedia page and take a look at that, and you see a couple of different sort of ranking of Bayes factors that you get from a 2x2 table that sort of casually guide the analyst after calculating a Bayes factor, which I'm going to encourage you to do. Give a guide to when you say there is a relationship and when you say there's not. When you say in Bayes terms that there seems to be evidence favoring one model over the other. It's done like this really. So this, you've seen this before. You're just making the matrix here with one line of very simple code. You can make another matrix and call it prior. You can call it whatever you want. It is just a matrix of ones. This is a sort of setting us up to make a couple of assumptions, Bayesian assumptions about that's probably not. We're going to assume a uniform prior here. This is no information going in. Just load the library. Might have to, probably certainly will have to load this package, download this package first. Learn Bayes is the capital. It's one word. But when you load it up, the capital letter L, the capital letter B, got to use that. It has a function in it called ctable, and so you've created these two matrices. Just type this ctable data prior. It'll show you that the Bayes factor here is 2.62. Refer back to the Wikipedia page, and you'll see that it's pretty solid evidence that the two are not independent in a true model-based comparison. I'm not going to walk through the mathematics here. Just wanted to give you the alternative, or in my view, is kind of sort of complementary way to examine this problem, asking the question of a limited amount of data. Here are 100 observations. Are these things related, or are they independent relative to, in this case, repeated sampling over time? In this case, a model-based comparison with priors. That's it. So what up next? It will be a sort of focusing immediately on the chi-square problem, what chi-square doesn't do for us. It doesn't tell us anything about the nature of the relationship. I mentioned this in the last video. It doesn't tell us anything about the direction of the relationship. You can't stare at a chi-square of 4. Chi-square is always positive. Everything square is always positive. You can't say anything about the direction of the relationship. You have to look into the table to see clearly here that it is women favoring Obama rather than men favoring Obama. So nothing about the direction, nothing about the strength of the relationship either. So we're going to move into a session of videos called Measures of Association. They begin to address those questions. Now we know statistically there is some relationship here. We'd also like to know something about its direction and its strength, looking at a number, a descriptive number. And so we'll look at a couple of different strategies for doing that. Chi-square also has this problem. So does Bayes factor. If you actually encourage you to run that and then run what I'm about to show you here. So we have 100 observations. Let's assume instead it's 1,000. And that everything else holds, the relationship holds out exactly the same way. So we're just adding a 0 everywhere. So I just multiplied everything by 10, right? That's all I've done. This Pearson chi-square here is 4 with 100 observations. Pearson chi-square here now becomes 40. 40, how statistically significant is that? I have no idea. I wouldn't even check. The p-value is going to be 0.00001, something like that. A ridiculously significant result from the frequentist perspective, illustrating also that chi-square is proportional to n. So it really is exactly proportional to n. If you sort of keep the same relationships interior and multiply everything by 10, you're going to get a result that's 10 times the size in the raw chi-square value. If when you make this matrix you make it 300, 200, 200, 300, and so on, you're going to find a gigantic Bayes factor. I wouldn't even guess at it. Maybe 6, 7 million, something like that. Gigantically significant. These are powerful relationships inside the cells of the table. Very powerful relationships that are not illustrated well with 100 observations. So we're going to look at measures of association in the upcoming set of videos and some strategies for finding and putting together some statistics that tell us more than simply whether these two things are related in repeated sampling or in the model-based comparison from Bayes. That's it for contingency tables and chi-squared.